All right, let's get started with a prayer. So, the egg liquor will not be graded. Okay, I'll explain in a moment. Who'd like that for a prayer for us? Thanks. So in winter semester, when I teach this class, when we start talking about series and power series, pi day comes up in about the middle, and right around the ratio test. And I actually get to spend some time talking about pi and approximations of pi. Pi is one of the 5 most important numbers in mathematics. So the egg collector quiz is just to see how many you can get. Write down what you think the other 4 are. Okay? And then I'll tell you what they are, and then you can click in. I'm just interested to see how many people get. So. No one can get 0. I already told you pi is one of them. So I guess you could get 0, but. Okay, has everyone got those written down? People are already claiming, 60% of you are already claiming that you have all 5. You're really confident. Okay, take 10 more seconds. Write them down. Okay. Someone tell me what they think another number is. E. 1. Not 10. 0. And I. So chime in. How many did you guys get of the 5? Oh, those. Okay. Except pi is for the letter P. But I guess if you wrote a pi upside down, it would kind of look like a U. So, Nico, did you have a question? Yeah, but you could also just say that -1 is a scaled version of 1, maybe. So. Yeah, it is. But I like your thinking. I'm not the one that decided this, so. Okay. So 36% of you got the correct, got all 5. 46% of you got 4 of the 5. Nice job. So, there you go. Okay. So I'm going to talk about the binomial theorem for a little bit. Well, we'll talk about a binomial theorem you've probably heard about before. So, okay, what's this? Pascal's triangle. What does it represent?
Second determine the coefficients.
Do you want to say that louder?
It's determine the coefficients?
If you take powers of 1 plus x, or some teachers will do x plus y, then it gets you the coefficients of the binomials. Okay? And there's formulas for these. If n is the power of your binomial, and r is the power of x, then the formula is n factorial over r factorial n minus r factorial, and if r equals 0, then then the power of x equals 1. Then this formula is equal to 1. So, then it works out really well. If r equals 0, you can see you get a 0 like a 5 factorial over 0 factorial over 5 factorial. You just get 1. So, but you can, let's start looking at this line right here, that fifth line. And let's simplify this formula a little bit. So you do get, in the first one, you just end up with 5 factorial divided by 5 factorial. The second term, you get 5 over 1. The third term, you get 5 times 4 over 1 times 2. Then 5 times 4 times 3 over 1 times 2 times 3. Okay, so I'm just applying this formula here to each of the terms, each of these terms. So this is a power of, this is x to the 0, this is x to the 1, this is x squared, this is x cubed, this is x to the 4th, this is x to the 5th. So I just started writing out those, and if you simplify them, this is what you get. Like, for example, on this one, if you do 5 factorial over 2 factorial times 5 minus 3 factorial, then you get 5 times 4 times 3 factorial over 2 factorial times 3 times, oops, I made a mistake, that should be 2 factorial, you get 3 factorial. Those cancel out, and you just get this much, and you get it right there. Yes? R is the power of x. So it's the term with that power, with the x that has that power. Okay? So if you keep writing these down, 5 times 4 times 3 times 2 times, that's it, 1 times 2 times 3 times 4, and then 5 times 4 times 3 times 2 times 1, 1 times 2 times 3 times 4 times 5. Well, that just becomes 1, right? And that is the exponent to this term, x to the 5th. What happens if you try to go one more time? Yep, you get a 0 in there. And you'll always have a 0 in there, so from there on out, your coefficients are 0. Because the pattern is you keep, so the reason I'm writing this is because we see a different pattern. We see a pattern going on, and if you continue that pattern and don't write it in the factorial notation, if you don't think of it as factorial, you just always think of this numerator as a factor where you're multiplying it by 1 less than the last factor that you had. Right, 5 times 4 times 3 times 2 here. To go here, I subtracted 1 from my 2 and then multiplied that on. So I subtracted 1 from the 1, and you get 0, and you multiply that on. Okay. So this works really well as long as you've got powers that are whole numbers, positive whole numbers, and it makes us really happy in college algebra. And you just get these, you only have finitely, if you have a power to the fifth power, you get 6 terms, and you're happy. Unless you're Isaac Newton. He was working on problems where he knew this pattern, and he asked himself, what if I don't have a whole number power to my binomial? For example, what if I have 1 plus x What if I have 1 plus x to the 1/2 power? Does this pattern still hold? What happens? What do I get if I keep doing this? So let's try this. First term is 1. The first coefficient is always 1. Seems to be. So first term is 1 plus, and then I have my power, which is 1/2, divided by 1 times x. And then I have my power times 1 minus my power over 1 times 2. And that's times x squared. Right, in the same way that we had the power and then the power times the power minus 1, Isaac Newton tries the same thing. And it's divided by 2. We're dividing it by 2. And then the power times the power minus 1 times the power minus 2 over 1 times 2 times 3 x cubed. And you get the idea. We end up with a power series. Before they were cool, Isaac Newton was doing power series. Okay, maybe you still don't think they're cool, but so he writes down this power series. Oops, that was cool. He writes down this power series and ends up with ways to approximate things that then was really hard. Things like the square root of 2. For example, if you plug in x equals 1, you can start to approximate the square root of 2. It is in the you do have to calculate the radius of convergence. The radius of convergence is 1. And it does happen to if you plug in 1, you do end up with an alternating series because you're multiplying by these. Every time out here, you're multiplying by a negative value. And so you end up with an alternating series. They are getting smaller. It does converge. And you can now approximate the square root of 2. And you can change it a little bit to get the square root of 3. Now the square root of almost any number, which in a pretty straightforward way. And then he does something crazy. Oh, maybe genius. He thinks of this circle, a circle that has a radius of 0.5, centered at 0.50, and he uses this to approximate this section of the circle, which he knows. He knows is going to be the radius is 1/5, so you have pi r squared, so not 1/5 but 0.5. 0.5 squared times that's an angle of 30 degrees over there, so pi sixths, so you end up with that's pi over 24. And but you can think about it another way if you know calculus, which
Isaac Newton helped to invent calculus, so he knows calculus. You can think about it as this piece over here and this triangle here. And the triangle's pretty easy, basic geometry. How about this curve? You do an integral. And you have to find an integral of this thing, 0 to 0 to 0.25, it's to a fourth, of the square root of x plus x squared. Now, if you and I were doing this, we would complete the square. Okay, maybe that's not what you would do, but that's the most straightforward way to do this. He thought about it this way, square root of x times the square root of 1 plus x. So he factored out the square root of x. This doesn't make it easier to find the antiderivative of. What he wanted was something of this form here. Oops. He wanted something of this form, so he could rewrite that as his new power series, and he could go term by term and find the antiderivative and do the math and connect it to this expression of pi and get really good estimates of pi. And so this binomial series was a huge thing. It allowed a lot of mathematicians and quants back then to start approximating things with high degrees of accuracy in a much more straightforward way than they had before. So 20 terms of the series he ends up with got 16 digits of pi. So, which was a huge improvement. So, and it was and they could easily just keep on going for as far as they wanted. So, okay, so let me give you guys one. Let me stop talking for a little bit. So find the power series. Oh, here, let me go back just a little bit. I should have talked about notation. These coefficients, like these coefficients right here, they're not really clean. They're not straightforward factorials. So they invented a new notation just for these coefficients. Okay? And you saw this in a book. I didn't see it until I was in your shoes, so I doubt any of you have seen this before. Maybe a few of you have. But NR is the coefficient for where this is the power of the binomial, and this is your power of x. So, for example, if you had 1/2 3, then that would be 1/2 times a minus 1/2 times a minus 3/2 over 1 times 2 times 3. So I can stop when I get to that number. So that's the notation for your binomial coefficients. Okay? So I'm sure you were as confused as me when I was reading that when I was in your shoes. So it makes it so you can actually write down the binomial series in a very slick way. You can write down the binomial series 1 plus x to any power k equals kn n equals 0 to infinity x to the n. So now you can write it down in a really slick way if you understand what that notation is. And these coefficients, again, though that k over n, those coefficients are, let me just write it out down here. This series is 1 plus kx plus k times k minus 1 over 2 x squared plus k times k minus 1 k minus 2 over 3 factorial x cubed, and you just keep on going. So that is the same as writing down k0 plus k1x plus k2x squared plus k3x cubed, etc. Okay? So use the binomial theorem to find the power series of the cube root of 8 plus x centered at 0. Then use the first three terms to approximate the cube root of 9. Okay? So that's your task. I'll write down the binomial series down here again. I guess I'll do it down at the bottom. So can you use what I wrote down over here? Okay, so if we know we have a form of 1 plus x to the k, we can start using the binomial series. So think about how you can get this into the form of 1 plus x to the k and write it down as a series, and use the first three terms of that series to approximate the cube root of 9. Go. So the binomial theorem is set up so that this first number has to be a 1. So you need to be able to rewrite this so you have a 1 to work with there. So factor out an 8 and rewrite it this way. And then before you apply the binomial theorem. Yeah. It's the way the binomial coefficient is defined, but it also fits the pattern that we saw here. Like those are always, first term's always 1. So. Yeah, thanks. Okay. So I did my work up here. You may have done this a little bit differently. It's fine. There's different ways to get to the same solution on this problem. So first I rewrote my cube root of 8 plus x as 2, because the cube root of 8 is 2. 2 times 1 plus something. That something is x over 8 to the 1/3 power. Then I just rewrote all of this. That's just the general binomial series. So I know if I have 1 plus something to the kth power, I can start writing it out as 1 plus kx plus, or 1 plus k times that something times k minus 1 over 2 times that something squared, and just keep on going. But in my case, k is 3, or 1/3. K is 1/3, so I'm going to replace k with 1/3. And I don't have an x. I have an x over 8. So everywhere there's an x, I have to replace it with x over 8. And I also have to multiply it by 2. So the way I got this expression is everywhere. Oh, dang it! I didn't replace it with x over 8, did I? Incomplete. There we go. So everywhere where there was an x, I now have x over 8. So I have powers of x over 8, and everywhere there was a k, it was 1/3, and then I can actually start solving there. And here was the general form, 2 times all of that. Any questions with that so far? Yes? Oh, this is number 1. We're finding the power series center to 0 first. This is A. So I haven't started with B yet. So, well, I've started. I got the work. But yeah, I'm just finding the general power series for that first. So, okay. There were some other questions. Were they the same? Oh, it's not. Hold on. It's amazing you guys learn anything in my class. With as many mistakes as I make. So, thanks. I did 1/2 as the example in my last class, so do that up there. Yes. Yep. Yep, the first term is always 1. That's k over k 0th, like this, the 0th binomial term is always 1. Okay. Okay. So now let's do part B. So part B is, let's take the first 3 terms. So 2, 1 plus x over 3 times 8 plus, or minus actually, minus 2/9 times 2 x squared over 8 squared. The 2's divide out. So these are my first 3 terms for an arbitrary x. What value do I plug in so that I'm finding the cube root of 9? So I'm not going to put in 9 here for x. I'm going to put in 1. So then I'll have that sum will be 9. So now now the cube root of 9 is about 2 times 1 plus 1 over 24 minus 1 over 9 times 8 squared. Okay? And that is, I have it in my notes. I plugged 1 in for x. Yeah, so that's 2.0798 something, 6111. But the cube root of 9, if you plug that into the calculator, we get 2.0800 8 something. So look at how close we are. The difference is 0.00022. So just 3 terms. You can imagine how powerful this was for someone like Isaac Newton to be able to quickly, well, not so quickly, actually doing the adding up those fractions and doing the long division may not have been so quick. But compared to the methods he had before, still, it was pretty straightforward from what they had. Yes? Yeah, so the 2 is right. Here's the 2. So that's just carried down. The 0th first and second term? Oh, so I said in the question, I just said find the first 3 terms. Not a polynomial of degree 3, or like not a 3rd degree approximation. So yeah, sometimes we'll say use the first however many non-zero terms to approximate things. So okay, any questions about this? Yes, Alex. That's the easiest way for me to think about it. But if you do a bunch of these, one is just the natural. Well, there's lots of different mathematical reasons why. This k choose 0 is the number of ways you can take a group of size 0 of k things, and there's only one way to do that, by not taking any. So that's another reason why you might just say that it's 1. Yeah, so there are other reasons why it works, or it fits a whole bunch of patterns you can come up with to say, hey, we really should define this to be 1. Yes, Joseph? So that works when it's a whole number. So it's right here. So, but when you're dealing with if you've got a power of 1/3 like we have, then we don't have a 1/3 factorial. Well, we sort of do. Did we talk about the gamma function in here? Yeah. So then you've got to start using the gamma function to do things. So okay. Well, other questions on that problem before we move on? Yes. So what was your question? I just didn't quite hear you. Okay. To find the cube root of 9 in my expression, this x has to be a 1. And so I just replaced x. Everywhere there was an x, I replaced it with a 1. So I replaced it on the right-hand side, replaced it on the left-hand side. And so then you just get 1 over 3 times 8, which simplifies to 1 over 24. Okay, great. So I did do that kind of fast. All right. going to write down the power series for e to the x. Sine of x, these are ones you should have memorized. Or you should have memorized before you take the exam. We will have an exam the week we come back. It starts on Wednesday, I think. It's on 11/3 to 11/11. I can't remember when it ends. Made a mistake there. All right, what do you notice about these? They all follow a specific pattern? Any connections you see between them? He said if you take the absolute value of the terms of cosine x and sine x, you get all the terms, or you get e to the x. So if we add those up, and you can see we've got a 1 here, we've got a 1 there, we've got an x there, we've got an x there. We have an x squared over 2 factorial there. Right? We've got these connections that we can start making. So let me write that out. Well, I'm going to just write out sine of x plus cosine of x and keep the signs in. So we're pretty close. The problem is those signs. Right? The signs go positive, positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative. You guys remember anything from your past that also went positive, positive, negative, negative, positive, positive, negative, negative? So powers of I also go positive, positive, negative, negative, positive, positive, negative, negative. So maybe we can make a connection here. What if I replace, instead of, if I throw in an I with the x here, then I'll end up with powers of I, and I end up with e to the ix equals 1 plus ix minus x squared over 2 minus ix cubed over 3 factorial. Because I had an I cubed, but I cubed is the same as minus I, right? Yeah, because it was positive. Right here, this I cubed, I can rewrite as a minus I. Plus x to the 4th over 4 factorial plus I x to the 5th over 5 factorial plus, minus x to the 6th over 6 factorial plus I to the x to the, that should be negative, 7th over 7 factorial Okay, how close are we now? We have this thing, and we have this thing. Are they equal? No. Are the signs right? The signs are right. What are we missing? We have an I on all of the odd terms. So we have an I here, an I here, an I here, and I here. Which ones are the odd terms from up here in this expression? Sine. One equation that connects all 5 of the most important numbers in mathematics. This is called one of the many equations called Euler's equations or Euler's identity. So pretty amazing. Yes. Okay. All right. This is amazing. This is incredibly useful. I know you guys think like imaginary numbers don't have any use. The first place that most students, math students, end up learning this equation here is in differential equations, which is the basis for applied mathematics. When you have differential equations that come out with imaginary solutions, then you actually use these equations to translate them into things that make sense, that are easier to get your head around and easier to model. And it turns out they come up with things that, whenever you have phenomena that are cycling back and forth or rotating around, then somewhere you've got e to the I tied in there. And for those of you that watched that video that I sent out, now it should make a lot of sense why they used e to the I theta to talk about circles going around. Because e to the I theta, all you need to do is plug in a theta. If you have a to the e to the I theta, you get a vector of length a and an angle of length theta on the complex plane, and it tells you where that point is. So as theta changes, you just make circles. Have a great day. Thanks, Brother Corey. You're welcome. See ya. We got to get to that today.
Oh, yeah. I haven't done that yet. I should do it. I want to do it in 112, but from a different standpoint.
Yeah.
It's like, what's the best math equation? What's the most beautiful math equation?
Well, I always start either like a day or two before. In winter, it works out better because then you can say right around Pi Day.
Oh.
You're doing series, and you can spend time talking about pi, and then it's like you can say, well, pi is one of the 5 most important numbers of mathematics. What are the other ones? Yeah. So we did that at the beginning of